record, and we're recording our meeting. So what we have been talking about is charge in matter and the relationship that charge in matter generates to other matter. And the really interesting feature of the interaction of charged matter is that it's very similar to gravity. Very, very, very. The mathematical formula which describes the force exerted by charged matter on each other is exactly the same as the equation that shows how gravity exerts force on masses. It's eerily the same formula. You just replace M with Q, where Q is the charge on the matter, where in the gravity formula, M was the mass of the object attracting one another. The other big difference is the magnitude of the proportionality constant that makes the two sides of the equation equal. The magnitude of the proportionality constant for gravity is super tiny, so that you have to be really massive to have any gravity force, whereas the connection of proportionality for force to the charge constant is huge, which means if you have only a tiny amount of charge, you get a substantial force. And what that ultimately means, ladies and gentlemen, is that all solid matter is held together by its charge relationship, not by its gravity relationship. Now, there's other really interesting things, at least interesting to some nerd like me, that stem from this fact that it was noticed that gravity and electricity had very similar equations of force. It led physicists to ponder whether all forces in the universe were related. And they were able to describe the various ways in which matter interacts with each other, how waves interact with each other. And they broke it down into several different kinds of ideas and formulas, of course, models for the behavior of electrical force compared to gravity force, compared to the forces that hold the nucleus together, and all these other things that make our universe cohesive. And what physicists have been searching for the last 100 years, and what drove Einstein nuts looking for this in the last half of his life, was what we call the unified theory. The belief is that there's a magic single equation that can describe all the phenomena of the universe. And a lot of people have dedicated a lot of time to build a model where we don't need a separate expression for electricity compared to what we use for gravity, compared to what we use for holding a nucleus together. And they call this the unified theory. And they have been able to unify a few of the forces. The things that cause radioactive decay has been able to be unified into the force of electricity, but they haven't been able to get one general combination of all the forces yet. And believe me, there's a lot of people working towards doing this. Okay, well, we of course are not here to study the unified theory of the universe, the singular equation that describes everything that goes on. What we're doing is just looking at the idea of electrostatics in terms of how it affects the behavior of matter around us. Now, what we saw so far is that charge comes in two flavors, I like to call them. And the flavors are plus and minus. And as I talked about on Monday, Ben Franklin had a big to-do with the establishment of using the idea of plus and minus. And as I went on and off about Ben Franklin last time, about what an incredible individual he was, truly a remarkable man. Not only, of course, everybody knows him in terms of his founding father status, but his endeavors in science and philosophy and engineering and invention, incredible. Just an incredible individual, really. But he is the original designator of positive and negative charge. And of course, you probably heard the famous story of him flying a kite somewhere in Philadelphia when there's a storm, and he hangs a tail that has a key on it, and the key gets struck by lightning, and he creates a current, and then then builds a model of the behavior of electricity from his experience in this experiment that he conducted during a storm. It's a legendary story, much like I earlier spoke of the legendary story of Newton sitting under a tree and an apple falls, and he came up with the idea of gravity. So whether or not the Ben Franklin kite story has any truth to it, I really don't know. I'm sure most stories are based somewhere in some truth, but I'm not sure of the veracity of all the details as to if that is exactly where he came to the conclusion that he needs a positive and a negative to describe the behavior. Now, another analogy I want you to take is the reason we have positive and negative as opposed to mass, which is only positive, is because masses only attract each other. This mass pulls this mass towards each other. So gravity is always attractive. And again, the weirdness of electricity is it can be attractive or repulsive. So kind of the sign has something to do with the direction of action that the push or pull will cause as a result of the action of this permeating force in our universe. Gravity is only pulling. Electric interaction can be pushing or pulling. Okay, so a little recap of where we were. What I want to do now is dive in to the slides, and what that means is I'm going to do my usual clumsy, like stand here and stare at what I'm doing for a minute. No, I'm hitting the wrong button, of course. I want to hit the present now button. And then I want to present my screen. And so I'm going to click on my screen, and then it should say I can do that. And it does, and I'm going to share. All right, so what I'm going to share, of course, are I'm going to share my PowerPoints. And there they are. So one more clumsy effort here. I should now have my PowerPoints up. And I believe, I'm getting old and feeble. I believe this is essentially where I left off. We had talked about charge distribution in matter. We talked about the way you can charge matter. We talked about the fact that only moving electrons around is going to describe how we're charging matter, meaning the protons are held together very tightly in the nucleus. So when you positively charge something, you don't do so by adding protons. Too energetically insane. When you positively charge something, you have removed electrons from it. Now, another interesting premise or thesis, if you like, that Ben Franklin again proposed was that there is conservation of charge in our universe. And what do we mean when we say there is conservation of charge? It means that all the charge is here. We don't create it or destroy it. We just move it around. And my analogy would be, again, when I drag my feet across the carpet, I touch the doorknob and I get a shock. The reason I do that is when I was dragging my feet across the carpet, I have scraped electrons loose from the carpet fibers and they are spread over my body. And if I build up too much charge difference between myself and the carpet, and we have a fancy name for that we'll probably mention again a little later, that's voltage, is this separation of charge from neutral. Something becomes negative while something becomes positive, and the difference in energy between the two is the voltage that you have generated when you've separated the charge. Again, charges start out equal, positive and negative. I start to separate the charge. One entity becomes more and more negative, while the other entity becomes more and more positive. And really this energetic difference between those two is what we commonly refer to as voltage. When I build up enough voltage and I get near a conductor, this charge says this imbalance is not favorable. I need to redistribute. So the charge can flow to redistribute. And I make a little arcing spark to the doorknob, and all that magically, very rapidly, everything redistributes. I become electrically neutral. The carpet becomes electrically neutral. Everybody's happy. Now, interestingly, too, the magnitude of this separation of charge allows me to flow the charge through a poor conductor like air from a greater distance. If I separate enough charge on me, I can be further from the handle, and the spark will arc further and jump to that handle a further distance. If I only have a little charge separation, I have to get my finger really close to the door handle before there's enough oomph or push of the energy of my separated charge to flow through the air and connect back so that the charge gets redistributed. This is why lightning bolts, of course, that's flowing miles of distance from the clouds to the ground. And if the lightning bolt can flow a mile in distance, the push has to be incredible because the air really does not want to conduct electricity. There's a crazy push. So that means there's an insane amount as the clouds rub against each other and rub against each other. There's an insane amount of buildup of charge in the clouds compared to the earth. And eventually all this redistributes when enough builds up so that it can force the air to conduct, even though the air doesn't want to. It takes an incredible amount of energy to do something like that. Okay, so materials like the air are natural insulators. Insulators are things which do not want to conduct electricity unless you really force them to. A perfect insulator, no matter how much voltage you apply to it, will not allow charge to flow in it. As a material begins to have the ability to allow charge to flow in it, it becomes a conductor. The less energy that it takes to allow charge to flow means it is a better and better conductor. And what it is conducting is what we call a current. And what a current is a flow of electrons. Electricity is a flow of electrons through something that allows the electrons to migrate through that material in its attempt to redistribute, in its attempt to balance everything. Everything naturally wants to be electrically neutral. We can use energy to separate the charges, but once they get so separated, they get very unstable, and then a natural redistribution occurs. So an insulator, as we're all very familiar with the term, a conductor, we're all very familiar with the term. So we talked a little bit, I think we did talk about this, now it's coming back to me, I guess. We talked about the fact that metals are the main conductors in the periodic table, particularly copper. That's the commonly used metal that electricians prefer. Why? Because it's a very good conductor, relatively abundant, and so we make most of our electrical wiring out of copper. Now, iron, if you remember our little table from way back when we began our discussion of the relative abundance of elements, iron is way more abundant than copper in the Earth's core, way more. So iron is way cheaper than copper. But the reason that iron is not used to make wire is that it's just not a very good conductor. Now, it conducts, don't get me wrong, you can get shocked if you have a slab of iron and you put it into, touch a bare wire on it, you will get shocked. If you touch a screwdriver, which has an iron paddle on it, on the end of the screwdriver, you stick it in there and touch some conducting circuit, you will get shocked. It's simply the fact that it's just not nearly as good of a conductor as copper, so that wiring is much more readily made from copper. Now, there's other reasons too. As a matter of fact, copper has better malleability, ductility, which means you can stretch it and bend it and shape it way easier. So you can make strands of copper wire so that, and then you can tuck them around the edge of the doorway and this and that, much easier than if you did try to do the same thing with iron. So iron has a lower conductivity and a lower malleability or ductility, stretching ability than a strand of copper. So copper is our go-to. Now, what I will tell you though is copper is not the best conductor of electricity. It's right, very close, but it's not the best. Other members of its family or elements in the same column of copper turn out to be even better conductors of electricity. Copper is in the column of the periodic table, which we call the coinage column, because the elements that are in copper's column have been traditionally used to make money. The stuff we trade for value when we do goods and services with each other. And those metals that are cousins of copper, I'm sure we're all familiar with, are gold and silver. They are really good conductors of electricity. They're actually very ductile and malleable. That's another reason why we have adored them for so long, because you can ornamentally shape copper and gold. Not only are they pretty and dazzly, they shape really easily. So they have those kinds of properties as copper does. But of course, the issue with silver and gold compared to copper is availability. Even though they are better conductors and they still bend real nice, just like copper does, they are just much rarer on the planet. And their rarity adds to their intrigue and adds to their value. So people don't want to use them so much to make conducting circuits because of the fact that they're so valuable. Now, I will tell you, if you buy the top end electronic devices, they very commonly make wires in those devices out of silver, or they very commonly make wires in those devices out of gold, believe it or not. And the reasons behind that is that they have very low resistance to the flow of charge. They don't heat up dramatically when electrons are flowing through them. Current flows through them very, very readily without much loss of energy at all. But for everyday normal devices that you and I are going to use, we typically use copper as our conductor. Okay, I'm babbling on. Let's move on a little bit here. Insulators, as we say here, are more averse to allowing charge to flow through them. Now, there's various degrees of insulation. Again, some materials have partial ability to impede the flow, while others are really good at blocking it almost entirely. Pretty much, if you have enough oomph, you can make anything conduct. That's for sure. You should keep that in mind. But it's just not worth, if the electricity can find a simpler path, it'll just avoid the insulator and take another path between point A and point B, going through a better conductor than that particular insulator. So typical materials that are insulators, some of them are probably familiar to you. Rubber is a good, I didn't really even list rubber there, but it's a good insulator toward electricity. We often coat our wires with rubber, or nowadays, of course, we coat our wires with plastics. Wood, it turns out, pretty good insulator. The problem with wood is, like, if you have a branch that's not dried and it has a lot of water in it, and the water has a lot of electrolytes in it, like a lot of salts and things that are naturally present in living things like trees. Well, these things are items that allow the charge to flow very, very readily. The same thing is true with water. Water is not really a good conductor at all, but it's when you have salts dissolved in water, these are charged entities, and charge flows readily through impurities that are dissolved in the water, just like it flows through impurities dissolved in wood as well. Okay, so and then lastly here, it says something about heat conducting and electrical conducting. They kind of go hand in hand with materials. If you're a good conductor of heat, you're typically a good conductor of electricity. If you're a poor conductor of heat, or you're an insulator heat-wise, you're an insulator electrical-wise as well. Now here I'm showing our friend the periodic table, And this periodic table is trying to give some characterization of the elements, and it's trying to give a lot of different characterizations to the elements. And what you should take from this is that there's several different colors here for the different classes of elements. The ones that we're most importantly talking about in terms of their ability to act as insulators are the ones that, as it says, are green, red, or orange. Now, why did they make them all green? Again, they're trying to show different properties besides just conductivity in this table. So the red ones are essentially in the far column on the right. Those are all good insulators. And then the green ones are kind of in the upper right-hand corner, but hydrogen is in the upper left-hand corner. It belongs with its buddies on the upper right-hand in this case. Then there's this one column right next to the orange column, which has some elements that have important properties that they like to delineate. They colored those orange. So the red, orange, and greenish looking boxes represent our insulating elements. The blue and the purple and the different shades of purple are the metals. So you see we call the green, orange, red ones non-metal. We call the blue, purpler ones, we call those the metals. So as you can see in the periodic table, the metals far outnumber the non-metals. And there's kind of a diagonal. If you start up at H and then build a weird kind of diagonal down to the bottom right-hand corner of the table, it kind of delineates the metals from the non-metals, the conductors from the non-conductors in the table. Now, again, I'm not, if I were to specifically ask you the properties of one of these, what you would do on the question is you would just get this table out and see if its box is green. If its box is green, it's not a conductor. If I asked you if manganese or Mn is a conductor, you look in there, you see the box is in the blues are conductors. It's pretty simple to use a chart like this if you are asked to determine what is a conductor and what isn't a conductor. Okay, now what happens if you place charge on an insulator? You can, okay, that you can deposit charge onto an insulator. So I'm demonstrating what would happen here when I would do something like that. So I dump charge first into the corner. And so this wand I'm holding, again, they used to call it amber. That was before they invented plastic, way back in the early 1900s when they were doing electrical experiments. They traditionally used this material that I discussed with you before, was petrified sap essentially, and it turned out that it was really good for holding a charge on it. Nowadays, we would certainly use a piece of plastic that we could do a very similar thing with. So let's say I have a charged plastic rod and I touch it onto a metallic sphere. And when I do so, I transfer a bunch of negative charge, which was originally deposited on the rod, onto the metal sphere. Now remember, according to Ben Franklin, charge is conserved. So if the rod is losing some of its negative charge, if the sphere is gaining negative charge, that means the amount of negative charge on the rod is decreased for sure. So we're not conjuring this charge out of thin air. If some is deposited on the sphere, it is lost to the sphere from the rod. Okay, so the charge transfers to the sphere, and let's suppose first on the left of the bottom, the sphere is a conductor. Conductors allow charge to flow readily through them. Since I deposited all the same kinds of charge, what instantaneously, now I'm not going to say instantaneously because that's probably not exactly true, but almost instantaneously, as fast as can possibly happen, that charge redistributes from the point of insertion, if you like. I inserted the charge on the upper left-hand corner of the sphere. If the sphere is a conductor, that charge is all the same sign. Those charges don't like each other. Those charges push apart, and that causes the charges to rush to the outer edge of the conductor. So the bottom left-hand picture shows the initial deposit of charge was in a local position, meaning all at the same spot, but very quickly it redistributes on the insulator so that it is spread as far apart as they can get from one another. Now, interestingly, if the air outside of that sphere, of course, the sphere is in contact with air, if the air was a good conductor, that charge would continue to migrate. It would migrate outward from that sphere. But since the air is an insulator, the charge can't migrate any further apart. It's forced to rush to the edge of the sphere and stop there. Now, I should also point out, if you had the ability to deposit enough charge, a crazy amount of charge, then the air itself, which is an insulator in general, it's not a perfect insulator. Eventually, if enough charge is deposited, the air will conduct. And I'm sure you've all seen science fiction movies where they show these metal spheres, they pumped enough juice into them, and there's all these dancing lightning bolts coming off the sphere. So again, if you deposit enough charge imbalance onto it, that charge says, we got to redistribute. We'll expend some of our energy to get off of here to get back to where we can be equally distributed all over the place so that everybody's electrically neutral. And so in that case, you can make air conduct. So air is an insulator, so we're only going to be depositing a limited amount of charge so that its rush has to end when it gets to the surface where the metal conducting sphere contacts the air outside of it. So the picture on the left shows what would happen to my localized charge deposited on an insulator, a conductor. It gets as far apart as it can. On the right, I'm showing if the sphere, instead of being made out of a conductor, is made out of insulator. Notice I'm leaving the charge exactly where it's deposited. So the insulator can become charged, but the insulator does not facilitate migration. So the charge stays localized. Now remember, these charges are trying to push each other apart. They're repulsive because they're the same sign. But because the material won't facilitate their movement, they, even though they want to push apart, are stuck in the same location. So the picture on the right represents how charge will redistribute on an insulator. Okay, so this is how we can negatively charge an object. Let's say something about what would you do if you wanted to be tricky and you wanted to positively charge it instead. What would I do? Would I hold a rod of positive charges up to that thing and touch the thing with positive charges? And then when I do that, would I distribute positive charge in much the same way that you're seeing here? Remember what I already mentioned. Positive charge is a little bit harder to deal with. Now, we can charge objects positively. So how can you get away? How can you do it without thinking about depositing positive charge? So here is a trick we can use to deposit positive charge. Okay, so we call the trick that you can use to make a positive charge, we call it induction. Okay, so here's how we can do that. We put a negative charge wand, same negative charge wand, near the sphere. Now this time, instead of touching it and allowing the charge to hop off and onto the other sphere, that's what we did before. We touched it and allowed it to hop off. Now I'm just going to hold it in space. Notice the middle picture to the left. I'm holding the wand in space that is negatively charged, but I'm not touching the conducting sphere. On the picture above it, I'm literally putting that negatively charged wand in contact with the conducting spheres so that they can just hop off, go ashore, and land on the conducting sphere. Now, if I hold the wand that is negatively charged in space away from the conductor, charge is still allowed to migrate within the conductor. And what naturally happens is the positives that are all over the place in that conductor say, wait a minute, we like that. We like the fact that this is, there's negative up there. We're drawn towards it. And likewise, the negatives will run opposite it. Now, so that's really what you should think of. I'm already making the claim that it's hard to move the positive around. Well, it's easier to move the negative around. So what we can say then is neutral atoms near the upper left-hand corner lose some of their electrons, and they run as far away from that negative one as they can. If they run as far away as they can from the negative one, they're going to run to the lower left-hand corner. So you don't touch the sphere with the negative charge, but you influence the negative charge to run away. So the negative charge runs all the way to the right side. Now, if I put a wire from the right side to the ground, those electrons that ran to the right side can even get further. They can run down the wire and get even further away. So the picture on the middle right shows the electrons running down the wire even further. And now what I have done is I've created an imbalance on the conductor. If I remove that wire, now there's since some of the negative ran away as far as it could, it can't get back, because now for that negative to come back, it would have to flow through the insulating air. In the middle right corner, the middle right, I have a conducting wire connecting the conducting sphere to the ground. That allows negative charge to run as far away as it can, and it will even run down that wire. Now, when I disconnect that conducting wire in the bottom left-hand picture, now there's an imbalance of too many positives on the sphere compared to the negatives. So now, as you can see in the bottom right-hand corner picture, all the positives say we don't like each other, we are repulsive towards one another, so we have to run apart from one another. So we can use the induction trick to create a positively charged object, and we literally use a touching trick where we allow the negative charges to directly transfer to the conductor if we wished to charge it negatively. Okay, so the next thing we want to talk about is this weird concept of the field. And fields are very important to physicists because fields of action are what actually hold you and I together, are what actually hold the planets together as they traverse this universe or our solar system, how they stick together constantly. We've been going around the sun allegedly for 4 billion years, according to what we kind of understand these days. So planet Earth has been moving around the sun for 4 billion years. Why in those 4 billion years hasn't it decided to stray away from the sun? It's not like the sun has reached an arm out to the Earth and is holding the Earth out there and maybe moving it around there. It's not contacting the Earth to move the Earth around the sun. So physicists had to come up with a different picture of the way in which we can envision force being transferred from the sun to the Earth to hold the Earth in orbit around the sun. And this requires what we call a field. And of course, we all have a connotation of a field. It might be where we grow corn, it might be where we play ball, But in physics, a field is a quantity that has a value for every point in space and time. And so it has a numeric value, and actually it's a vector quantity. I wish I would have put that word in there. A field is a vector quantity. It has a magnitude and a direction at all points in space and time. Now, they might not be the same magnitude of direction or magnitude. Well, they're probably going to be the same direction, but they can have falling off magnitude, and pretty much all fields do that. The strength of a field falls off with distance. I'm not saying the direction is going to change. The direction of action of the field will always stay the same from one point, as long as you go in a straight line between your reference measurings, and we'll see what we mean by that. So as I move further and further away from an object that is causing a field to occur in space, then I'm going to have a less and less and less attractive pull or repulsive push from that particular object. So fields fall off as you travel through space. Now, what do physicists think fields are doing? They are literally, and this gets bizarre, they are literally altering space. Fields change this stuff that we exist in. Space, of course, is a bizarre concept, trying to think of what it really is and what it means for there to be this area. Well, I hate to use the word area to describe it because it's not an area. It's got 3 dimensions to it. But this X, Y, and Z location that we exist in is what we are deeming space. And what we're saying is that when a field is acting through that space, it's in some way altering that space. Now, I gave an analogy trying to describe what this means earlier, and let me remind you what that analogy was. When physicists, and in particular when Einstein, came up with a new improved model of gravity, Newton had described gravity in the early 1700s pretty well, and it lasted for 200 years. Along came Einstein 200 years later and didn't completely alter it, because a lot of what Newton said was right, but he modified it and improved it with this description of gravity now affecting literally the space of the universe. It alters space in the universe. And the model that Einstein came up with, which is a very clever model, is this. Instead of taking space as 3 dimensions, let's make space 2-dimensional for a moment. And then we can describe it as like a bed sheet. So space is now a bed sheet. And we put 4 strong individuals at the corner, and they stretch the bed sheet as tight as they can. So that is now space. Now, what gravity does to space is as if you put objects onto that bed sheet. Some of the objects are more massive than others, so some of the objects will make bigger divots in the bed sheet than others. Some will hardly even, so many will not even be able to make a divot in the bed sheet. So you lay some ping pong balls on there, and they just kind of sit right on the surface of the bed sheet. Put some bowling balls on there, and they make pockets that sink the bed sheet locally. Well, this is how Einstein described gravity. He said that the gravity pull of certain objects in space, and the more massive that object gets, literally starts bending space. And scientists immediately said with this model, well, let's go look for proof of this model. And they looked at how light traveled through space. And what they realized is that here on Earth, when I shine a tight laser beam, it literally goes linear, completely straight. But what they noticed in space was as light passed by objects, it started to curve. And the more massive the object that light passed by, the more dramatic the curve became. And Einstein even went further and predicted that when stars collapse, they become so massive that they are literally are so heavy on the sheet that they're making a hole in the sheet. And now things that come towards that hole just fall into that hole. And so he proposed this idea of the black hole, from which meaning that no light can come out of it. It's so powerful of a pull that light is forced to fall into this hole, and you can no longer see the light that emanates as if it's trying to pass the black hole. So that is maybe not perfect, but that's a simple picture that I think you can take from this story to understand what the words I'm saying here of how a field alters space. Think of your bed sheet, and think of your bowling balls, and think of your ping pong balls. And that's kind of the picture you can take for how gravity is altering space. Now, other things create fields. Electricity and magnetism create fields. So in some way, a charge in the back corner of the room can affect a charge in the front corner of the room, depending on whether they're the same charge or opposite charges. That might be a repulsive or an attractive pull for one another. So in some way now, instead of the mass of them causing the divot, it's the charge on them causing this divot in space. And now an object, if I have a really massive one here, it causes this divot. Look what it does to the other one. It just naturally wants to run to it. Okay, now that works for masses. Doesn't work so much for charges because some of them actually run away. But it does work for the picture of the masses, not so much for the charges. Some charges repel, some charges attract. Okay, so charges can create this condition in space. And now the interesting point about light is that light is all that it is field. Light is an electric field oscillating plus to minus. As this does so, it's a transverse wave, meaning it creates a disturbance this way, up and down, as it moves left and right, left and right. But that changing electric field makes a changing magnetic field. North-south, north-south, north-south. And a changing magnetic field makes a changing electric field. So the electric makes the magnetic makes the electric makes the magnetic, and they're both altering space as they fly through space. Now there's no matter in deep space, but they still fly through the space itself because they're altering the space itself. So these fields create, as we say, a condition in space that generates action at a distance. Now, to point out what that's kind of meaning, I want to move this paper towel roll. I must touch the roll to cause a force to act on it. If I am not touching it, and I can't do it without touching it. If I'm not touching it, I can't influence it to move. Now, it would be really cool if I could just do something like this and make it come to me or make it move for me. If I could generate a field, I could create an action at a distance that would enable me to do that. I must contact this object to apply force to it. The Earth doesn't have to, and here's what the Earth can do to it. Look, the Earth moved it without touching it. The Earth has a field which allows this to feel a force due to the Earth. Okay, so fields are conditions in space, and fields are electric or magnetic or gravity. Those are the ones that we're most familiar with. Crazy physicists have come up with other ones, but these are the only ones that are relevant to any discussion we might want to have. And they can work without touching an object, whereas the things we want to exert forces, or a car wants to exert force, or a bulldozer wants to move Earth, it has to contact you, I, or the Earth in order to move it. Okay, so, it says at the bottom, it says something about these fields can be vector fields as well. Gravity has a direction. again, when I drop my paper towels, they don't go upward. They have a direction in which they move. If I drop some other object, which there's nothing here I want to drop. Let's get something else. I drop this object, and I drop this object. Notice they both move in the same direction because the gravity is pulling them both in the same direction. So there's a direction and a magnitude associated with the action of these actions at a distance. Okay, now again, I want to say a few things about what gravity is doing first, and we'll say a little bit about what electricity does as well. So if we assume the Earth is spherical, hello? I don't know what's happening. I never get anybody on my phone except my wife. That's not my wife. Took care of that, I think. No, I better get that out. I'll forget that. Hold on, wait 1 second. Oh, I think I can turn this off. Stopping. Did I do that? Okay. I managed to push the right button. I must have butt dialed some commercial. Back to the lecture at hand, as Snoop once said. Assuming the Earth is spherical, objects on its surface have a force generated on them. And it's as if all the Earth's mass is concentrated. Okay, so if you're standing on the surface of the Earth, you are, of course, being pulled inward towards the Earth. If you're above the surface of the Earth, you're being pulled inward towards the middle of the Earth. Now, why does the Earth pull you as if it's pulling you to its middle? Well, okay, I guess I showed that. I'm sorry, I thought I showed that on this slide. Here I'm showing Newton's formula, and once again, please let me remind us, we're not using the formulas. We're not putting numbers in the formulas. We're just going to talk about the results of putting numbers in the formulas. So if you recall, it's something like it's proportional to M1, M2, and it's divided by the distance between them. So if you are standing on the Earth, the force an object feels on the Earth would be equal to G, the gravitational constant, times the mass of that object, whether it's you, me, a car, or a feather, times the mass of the Earth, divided by the radius of the Earth squared. And when you put all those numbers in, you will get the force that you feel on the surface of the Earth. Now, notice that for all objects out there, the mass of the Earth is the same, whether it's me, you, or a feather. The radius of the Earth is the same, whether it's me, you, or a feather. And the gravitational constant is the same. As I told you, that's the universal number G. It's the same, whether it's me, you, or a feather. So we can gather G, ME, and RE squared into one other variable I'm going to call A, because that's what it is. It's the acceleration that the Earth causes on you. So your force is your mass times your acceleration. But in this case, the acceleration is what is caused by the factors mass Earth times G divided by radius Earth squared. And believe me, scientists have fooled around with that number, and they have multiplied that number out, and we know what it is. It is the acceleration of gravity. If you take 6.67 times 10 to the minus 11th, which is G, times the mass of the Earth, which I don't really know off the top of my head, it's something like 10 to the 24, it's big. And you divide by the radius of the Earth, which is, I don't know, I'm going to say 10 to the 6th, 10 to the 8th meters. I'll go with 10 to the 8th meters. But people know that number too. Put all those numbers together, you get a value, which is the acceleration of gravity. And we often call that number G. And I thought I had G written there, but I guess I don't. Oh, I did. Well, I did it here. I actually put the numbers in. I guess this will show us the mass of the Earth. The mass of the Earth is about 6 times 10 to the 24 kilograms. That's a lot. The radius of the Earth, I was a little off. It's 6.37 times 10 to the 6 meters. Okay, a little off. And G is the number on the top left of that equation. Now again, as I said, we don't have to know how to put the numbers in. We're not going to put the numbers in. But if you put these numbers in, what you would get is 9.83 meter per second squared, which is the acceleration of gravity in SI units. Now, we would probably prefer, I thought I put it there, but maybe I didn't. Did I put it? I did. I put it underneath. It's underneath my little symbol there. The acceleration in gravity in more familiar units is 32 feet per second squared. So to us, that's what the acceleration of gravity is in the English imperial units that we're familiar with. 32 feet per second squared. Now here's what that number means. Let's say I'm up in the sky and I'm sitting still and I'm not moving. I'm going at 0 meter per second. Gravity is accelerating me at 32. I'm going 0 feet per, let's go with feet per second. I'm going 0 feet per second. But gravity wants me to go at 32 feet per second squared. What does that mean? If I start to fall from a speed of 0, after 1 second, I will now be going 32 feet per second. Because the value 32 feet per second squared means every second you accelerate by an amount 32 feet per second. So after the end of the first second, I started at 0, I'm now going 32 feet per second. If I fall for more time, at the end of the second, I have picked up speed by that same amount. Every second, I gain 32 feet per second. So at the end of 1 second, I'm going 32 feet per second. At the end of 2 seconds, I'm going 64 feet per second. At the end of 3 seconds, I'm going 3 times 32 feet per second. That's 96 feet per second. Every second, I gain 32 feet per second because that's how gravity accelerates me. So if I drop this paper tiles and I let it go high enough, this is not high enough so that it could fall for 3 seconds. At the end of the first second, it would be going 32 feet per second. At the end of the second, it has sped up by another 32 feet per second so that it is now going 64 feet per second. At the end of the third second, it is now speeding up again by that same amount, 32 feet per second. So by the end of the third second, it's now moving 3 times 32 feet per second, or 96 feet per second. Now this would go on forever if there was a vacuum on the Earth, if there was no matter in the way to impede or resist the motion. Air causes friction. And eventually what happens is the air pushes back so much that the acceleration comes to a limit. One place, of course, you've probably seen something like this is when you have re-entry of the shuttle into the Earth's atmosphere. It gets crazy hot from the friction that is built up. It's like rubbing your hands across the carpet. Your hands would kind of burn by doing that. You're getting the same kind of frictional resistance as objects fall through a medium like air. Again, vacuum, every second you'd increase 32 feet per second. Air, you increase, but eventually you come to what's known as the terminal velocity. You can't fall any faster because the air is pushing back with a force just as hard as gravity is pulling with a force. So those forces balance, and you can't accelerate any further, which is kind of cool. But again, we're really not here so much to play so many games with the numbers. I'm certainly not putting them in the equation. But I think one thing I would like you to know is that if you fell every second, you would gain a speed amount of 32 feet per second as you fall. That's what the implication of the acceleration of gravity is. Now, what we can do is the same thing with the electric equation. The electric equation was K Q1 Q2 over R squared. Now you factor out the common values that are affecting Q2, and those are K, Q1, and R. And we can call that the electric field. You can have an electric field just like you can have a gravity field. Now, this does not have a fixed number like the Earth does. The Earth has a fixed gravity field because the Earth has a fixed mass. You can put a different amount of charge, different number Q1 in there. The radius of the Earth, if you're standing on the surface, is always the same. So as long as you're standing on the surface of the Earth, me, you, a car, a feather, we are going to be feeling the same pull of gravity because we're all the same radius outward from the center of the Earth. But in space with charge, R can be varying again as well. So Q can vary in this magic equation. R can vary, whereas in the gravity acceleration equation, they're stuck. They're stuck to be the values of the mass of the Earth and the distance to the middle of the Earth from the surface. Again, we are not here to put numbers in. I just wanted to point out to you that this equation is very similar to the equation for a gravity field, but now we're talking about charge instead of mass. That's really the difference. And the value G is different than K. That's the other big difference. Okay, so let's just look at these two little equations again. One is for their force, then one is for their field. So you pull out those terms and you get these equations for their fields, and they look, again, eerily similar. But having said that, again, no numbers, you will never see these equations again, is what I'm saying. I'm just showing you them to give you the sense that gravity and electricity have very similar characteristics. I don't either care about the units of them either. I don't care. Don't care that you know about it. Not gonna ask you about it. Now, let's return though to this concept of the attraction to the Earth. Remember I said that to understand your attraction to the Earth or any object, not just you, all objects on the surface of the Earth are accelerated by 32 feet per second. Anything, me, you, a baseball flying through the air, this roll of paper towels I'm dropping, we all have the same acceleration of gravity. So this number is the same for everything, but why? I understand why it uses the mass of the Earth. I understand why it's using G, but why did I use the center of the Earth distance squared? This cartoon is going to try to explain to you why. In actuality, when you are standing on the surface of the Earth, you're getting pulled by every fragment of the Earth. So really what you should do is divide the Earth up into all of its matter, measure the distance of each piece of matter in the Earth from you, and then build this equation for the attraction you're feeling for each little bit of the Earth. And of course, each little bit of the Earth has a different value of R. So there's a piece of the Earth in South America that's pulling on me here in North America. That's certainly further away from me than a piece of the Earth in China that's pulling on me as I stand here in North America, or a piece of the Earth in Europe as I'm standing here in North America. All these would have a different R value if I did something like that. So what if you can do is just divide the Earth up into a bunch of little fragments, then look at the distance all of them are pulling over, then you average the distance to all the different locations that are pulling on you, since the Earth is nice and symmetric, nice and round, the average distance of all slices of matter pulling on you all over the Earth is, because of the symmetry of the Earth, right in the center of the Earth. So it's instead of worrying about mass in Iceland pulling on me, plus mass of Canada pulling on me, plus mass of Saudi Arabia pulling on me, I can just average everything as if all the Earth's mass is at its middle. Because on average, that's where all these distance vectors would be emanating from, the center of the Earth. Now, this actually makes a very interesting point, though. If you tunneled into the center of the Earth, and you could live in there, which you can't, but let's just pretend you did, what kind of pull of gravity would you have if you were standing in the center of the Earth? Well, the answer is you'd have zero pull. Why? Because all the Earth outside of you is pulling on you, but there's equal and opposite pulls from all the chunks. Like, put a chunk in, say, Europe, and then go over to a chunk in on the complete opposite side of the globe. They're each trying to pull you equally and oppositely from opposite directions. So if you were magically able to get to the center of the Earth, then there wouldn't be any pull from the Earth anymore, because all the individual pulls that I'm drawing, like I did in the picture above, the top picture, they'd all cancel one another. Some of them would be pulls while others are pushes. And all the pushes and pulls are equal and opposite. So when you sum them all up, you're going to get zero. From the way this picture looks, they're all pulls. And they're all pulls as if it's one average pull from the center. Now, what this ultimately means then is that if you're out in space, everything is pulled through the Earth towards its center. Everything. So if you're in an airplane flying above the surface of the Earth, you are still being pulled to the center. If you're in a rocket a couple miles above the surface of the Earth, you're still being pulled to its center. If you're on the moon, and the moon, of course, orbits the Earth, you are still being pulled towards the Earth's center. So the field lines is what we will call them. The field lines which describe the direction of action of the Earth's field, or remember, this is action at a distance. If you are off the surface of the Earth, everything off the surface of the Earth is being pulled to the middle of the Earth. So all these field lines are directions of actions that all point right into the middle. Now, I should have continued those arrows and let them meet in the middle. Then they would look like the spokes of a wheel. So that's pretty much what you should think of them as. They radiate outward like wheel spokes. Now, here's another weird thing about this. Because the Earth is so huge, the Earth appears flat. And I think I mentioned this already before, that when I now take two objects and drop them, because the Earth is flat, they don't come flying in towards each other. They go like they're going straight down. All objects fall from the surface of the Earth straight down. And what you should take from that is, if you look at the picture above, all those spokes or lines of gravity pull intersect the face of the Earth perpendicular. So if you drew a flat line touching the surface of the Earth, all those incoming gravity pulls are perpendicular to its surface. And since the surface is so big, we can't even see the curvature when I look out through town, and even when I'm looking out over the ocean, I can look as far as I can, have a really hard time noticing any curvature to the surface of the Earth. All the gravity pulls are coming straight down to the surface of the Earth, so they all appear as if they're coming straight down parallel to one another, as I'm showing in the bottom picture which is partially obscured by my stop the meeting or stop the presentation button. So we just envision gravity as pulling straight down to the surface. In actuality, it's pulling straight down to the center of the Earth, is what you should take from that. All right, so let's notice how the gravity field falls off. The Earth's gravity field falls off as a function of the square of the distance you are from the center of the Earth. So if you're at its surface, you have a gravity field that we're going to call G, just a number G. So you calculate G by putting in the mass of the Earth, the radius of the Earth, and the universal gravitational constant. Now, if you go out a distance 2r, so now instead of going out r, I went out 2r from the center of the Earth. So I'm an equal amount above the Earth that I am to the center. Now, how far would this be? Let me back up and recall this number. The radius of the Earth was, I thought it was on that slide. It's not on that slide. It's on one of these. Oh, there it is. The radius of the Earth is in the denominator of that equation. So when you're standing on the surface of the Earth, you are 6.37 times 10 to the 6th meters above the middle. So you're 6,370,000 meters from the center of the Earth when you're standing on the surface of the Earth. So what I'm saying then is if I plug 6,370 meters into this equation, while you're standing on the surface, with the mass of the Earth and G used in this equation, I'm going to get a number. And I'm going to call that number G, and it turns out that number is 9.8 meters per second squared, or 32 feet per second squared. Now, let's say I go up another 6,370,000 meters above the surface of the Earth. So I went that far up into space. So now the distance from where I'm in this orbit to the center of the Earth is as if it's 2 radii. So it would take 6,370,000 meters to get me from the surface to the middle, but I have now gone 6,370,000 meters above the surface. So I'm a distance 2r from the center of Earth. If I put that number in the formula that you see at the top, I'm now going to put 2r in the denominator, but I have to square 2r. Squaring 2r is 4r squared. And the difference in that number that I would get compared to the original number is 1/4 as big as the original G. So if G was 32 feet per second squared, and I went to another radii above the surface, so I'm 2 radii outward orbiting the Earth, now I'm going to be being pulled at 32 divided by 4, or 8 meters per second squared. I'm losing the gravity of the Earth. What are we saying? When you get up in space, you start to feel weightless. The attraction of the Earth is not as strong. So I will be weightless in space because I'm far enough away so that the gravity is not pulling me near as hard, because the factor of r in the denominator is getting so huge. Now I'm going to tell you, that's far. 6,370,000 meters above the surface of the Earth, the pull of gravity is 1/4 that it is on the surface. Now let me do some rough justice here. 6,370,000 meters, I divide that by 10, that's 1,000, that's roughly 2,000 miles. So I'm out there, okay? I'm out there. If I want gravity to fall off that much, I am out there if I want that to occur. Okay, if I went out 3r, So again, it's a distance r to the center and another distance 2r to get to the 1/4 g. Now I go a third r out. So it's 3 r's, or 3 times 6,370,000 meters to the center. I put that radius into the g formula. Now, because it's a factor of 3r and I square it, that's a factor of 9r squared. Or g at this distance will be 1/9 what it is at the surface. And that would make it something, if it's 32 feet per second squared, probably about 3.4 feet per second squared you'll be falling at. You're becoming more and more weightless the further and further out you get from the surface of the Earth. So the strength of the Earth's field falls off as the square of the distance you are from the Earth, and it doesn't make any difference what angle you make. It's going to be the same fall off as long as you're on the surface circle that matches that fall off. Okay, now what we're going to do is we have these lines which describe the pull that the Earth exerts. We're going to use lines to describe how charges pull. But because there's two flavors, we can't just have pull, we have to have push. So if I have a positive charge, I'm going to call it a push. If I have a negative charge, I'm going to call it a pull. That is the difference. With masses, I only had one direction, pulling only. Because now I have to deal with the fact that electric forces are either attractive or repulsive. I literally have to have two kinds of field lines, pulling and pushing. And I decided, now really it was this decided by convention. We could have done it the other way, but we didn't. We decided that we're going to look at this relative to what would happen to something that is positive external to the puller or pusher. So if you're a positive charge, you would push away another positive charge. So field lines emanate radially and from the center, just like for the Earth. They're as if they're coming from the center of the charge, and they push circularly outward like spokes. And if you're a negative charge, they still do the same thing. They move circularly out, but now instead of moving circularly out outward, they're actually moving circularly inward. So negative charges will pull, where positive charges will push, so that we can account for the two kinds of action. All right, I think we've had enough of this pushing and pulling. What we're going to do next time is we're also going to do some things with magnets. So I will have some slides, I think they're maybe already posted, about magnets. We're going to talk a little bit about magnetic behavior of matter. So you might want to get those slides if you like, or you can just look at them while we're playing along. So again, when I'm finished with some questions I'm going to ask you with regard to these, with no formulas to put the numbers in, at least not put numbers in, but maybe get some general ideas about how the formulas work. I'll be posting that soon. All right, so peace out.